Now I'm going to focus on to how to teach the Newton's second law. My presentation consists three parts. The first part is the context. I consider the level of student is a medium, and they are familiar to the inquiry-based learning method and apparatus. And the second about the objective of lesson. I hope that after learning lesson, students can understand the Newton's second law. As you know, the Newton's second law is stated that the acceleration of an object is the same direction of the net force acting on it, and the magnitude of acceleration is directly proportional to the net force acting on it, and inversely proportional to the mass of object. And I can express this law as vector A equal to vector F per m. And I also hope that students can have a four skill. First, they can design the experiment, they can record data and determine the error, and finally they can compare the result of experiment with the prediction. And third part, I will talk about teaching. Okay, we have a three phase. In the first phase, I will give some example for students. In July, for example, when we push an object, and it is clearly that the direction of an acceleration is the same the force we act on it. So they can realize there is a relationship between the acceleration and the net force as well as the mass. So the question is, what is the relationship between the acceleration of an object and the force and the mass of object? So to solve this problem, I will ask students comment the example in the first lesson. So it is easy to see that the acceleration is directly proportional to the force and inversely the mass object. Then I will introduce with them the Newton's second law. This is the law represents the relationship, and we have this formula. So now to verify the law is true in the life and experiment, I ask students to verify the law. So we have two cases. The first case, we have to verify the acceleration A directly proportional to the force when we keep the mass unchanged. And the second, we have to verify A proportional to m when F is constant. So I will ask students some question is what variable are involved, what to keep, what to change, how to measure, and what variable we have to measure. I think the student can answer in the first case, we have to change F and keep mass is constant. In the second case, we have to change M and keep F constant. Then I will introduce students the design of experiment. We have an air track. We can adjust its horizontal direction by adjust the screw. Cards in the air track, and the air track is connected with the air pump like this. And We stack a light barrier in the car, like this. A pulley in this, and we have a string which is connect with the car and the pulley, and we have a mast like this. We have two photo gate. We have to make sure the position of the first photo gate is as close as possible to the position of cars to make sure the initial velocity equal to 0. So we connect with two photo gates with a digital timer. We choose the timing tool to measure the time interval. The car moves from the first photo gate to second photo gate. So we have to measure A, up and M. Since the initial velocity equal to 0, so we can calculate A equal to 2s per t squared, in which s is the distance between two photo gates. T is the time interval the car moves from this, and we calculate the up. Since the system of objects move without friction force, so we can consider F equal to the gravitational force of the hanging mass. And about the mass, we can measure by balance. And balance. We consider the system consist of two objects, so F will equal to P. Since we have the acceleration.
You wrong, totally wrong. Write down the second, Newton second now for pulling object.
I'm one, two.
Yeah.
Okay.
Write down second Newton second now for M1. Yeah.
Yes.
Write down.
We have a P F T. M1, A1, and we have a T equal to M2, A2. Since A1 and A2 equal, so I can have to plug that with M1, M2, A equal P. The next first.
T equal to A or not? Or T?
No, it's not equal, because if equal then M1 will don't move.
Yeah, there's a problem with denotation in this case.
Yeah.
You use the wrong denotation for the figures. You denote F equal P and you denote F as the tension of the string.
Yeah.
And that's wrong. And I know you meant for different things, but that is a mistake. Go forward in denotation. Did you get the point?
Maybe you are not wrong, but you might be wrong.
You were already, what is F in the figures? F?
Is this?
Yes.
It is a photogate.
F or T?
This is
Okay, so what
that
is
is T.
T or F? Yeah. F. Yeah.
Tension. And F you use in the formula over there. It
Is a
external force on the systems. And F you denote here, over there in the figure, is a tension force. That is two different things. And you use the same symbol to denote for that.
Yes.
Okay, you get the point?
Yes.
30 seconds to do the experiment.
Yes.
You have to learn how to distribute the tone to the important things. 10 seconds.
Oh. Okay, I'm sorry. Yes. Repeat.
Do you record that number first?
Yes.
Please again.
Rồi. Yes. Here are the results.
Can you record it on the board? Why is it different?
I think the reason for the difference is we don't make sure the position of the first photograph is close with the
And read again.
again. Okay.
Do it again one more time.
I think it is enough.
No, let's do it. That's what's up to do it. No way to repair it. Even you don't understand why, let's do it.
Doing, let's understand.
I think the reason for the difference. I think the reason for the difference is maybe the air in the air track is not uniformly, and the pulley in this is.
The point is, in race, it's quite fun. Can you turn off the whole thing and do it one more time? No, turn off the whole, turn off the GC.
Yeah.
And do it just one more time.
No, no. Yeah.
Yes.
Yeah. I want to see that. Do you realize why?
I think the problem is the pulley. Since the pulley not fit.
Even I
I think still so I think the
different position to let the cast out.
I think the problem is the air track is not horizontal.
No, the first position when you let the cast out,
It is
you
true.
must mark the position, and each time the same position.
Same position.
Not this time in this position, and next time you
Change
again with other position. Not good.
Okay, so in this case, you cannot ensure that the initial position of the car is right away before it crosses the photo gate, but you have to make the consistency manipulation by marking the position you think that best possible to right before the photo gate, and many times you repeat, you have to put the cars or the bar at that position, and then you measure time and you calculate average time and so on. But the initial position must be consistency. There's only one point before the photo gate, and you have to calculate as more as possible that position compared to the photo gate.
Yes.
When you prepare for the experiment, and then you have to mark that position somehow on the ruler or on the chart, and when you do the real performance, you make consistencies data, not a ladder. But okay, I think it's quite fair to, because the time is in milliseconds, and
Yes.
and I have a few comments. I like drawing, and for me, this drawing is not acceptable. It's terrible. The strings should not be a curve like that.
Yes.
No way. How can you fix it? Fix it. Okay, and in the situation you provide to students is about if you add a bigger fork, you see a bigger acceleration. For me, it's very difficult to see the change in acceleration. We can see the change in position. It means we see the velocity. And we can see how big velocity or how small velocity. But it's very difficult to see how fast the velocity changes. And because you stay very confident, it is easy to see the change in acceleration when we act a different force, and that is not realistic. Think about another example where we can, or another expressions where we can still elicit somehow the relationship between F and A, but in a different way than the way you did it. So,
I think
yeah.
If a student can rely by example in July, I will make them do experiment.
Even in experiment, you can also see vividly the change in aspects. Data tell us about that.
Yes.
So you can start reasoning with maybe the graph problem. You can show student graph, velocity time graph of the objects under different force, for example, and you see different slope of velocity and so on. So it seems more realistic to approach to the problem rather than to show that we easily see the change in aspects in this one.
Yes.
So, okay, move.